Last time, tensors were just containers. We reshape them, slice them, move them around, but a container that can't do anything is just expensive storage. So today we make tensors compute. By the end, you'll do element-wise math, multiply matrices, collapse a whole dimension into a single number, and the part that trips up everyone, you'll be able to look at two mismatched shapes and predict what comes out before you ever run the code. Start with the easy case. When two tensors have the exact same shape, every operation just goes cell by cell, add them, and position 1 1 adds to position 1 1. Multiply them, same thing. Same shape in, same shape out, no surprises, no rules to memorize. This is the floor we build everything else on top of. Most of what you'll write looks exactly like normal Python math, plus times and functions like expol run element-wise across the whole tensor at once. You never write a loop. One symbol and a million numbers get the exponential applied in parallel. That no loop feeling is the whole reason tensors exist. Then there's the one operator that earns its keep, the @ sign, matrix multiply. This isn't element-wise, this is the actual workhorse running inside every single layer of a neural network. When a model does a forward pass, what it's really doing thousands of times is this one operation, a matrix of inputs times a matrix of weights. Matrix multiply has exactly one rule you must respect. An A by B matrix times a B by C matrix gives you A by C. Look at what happens. The inner two numbers, both B, have to match and then they vanish. The outer numbers A and C survive and become your answer shape. Inner must match, inner disappears, outer stays. Memorize that and you'll never guess at a matmul shape again. Now reductions, collapsing a dimension down. Sum and mean both take a dim argument, and the trick is which dimension disappears. Dim equals 0 collapses down the rows. You sum each column and you're left with one row. Dim equals 1 collapses across the columns. You sum each row and you're left with one column. And keep dim true. It leaves a size 1 stub where the dimension was instead of deleting it, which feels pointless now, but saves you constantly once you start broadcasting the result back. Which brings us to broadcasting, the rule that lets a small tensor stretch to fit a big one. Line up the shapes from the right, compare each dimension. If they're equal, fine. If one of them is 1 or missing, that one stretches to match. So a length 3 bias added to a 4 by 3 matrix. The bias quietly copies itself down all 4 rows. You never wrote the copy, PyTorch did it for free. But the moment your shapes don't line up, PyTorch stops and tells you exactly why. We'll trigger it on purpose. Add a length 4 vector to our 4 by 3 matrix and read the runtime error calmly. It literally tells you tensor A is size 3 and tensor B is size 4 at the mismatched dimension. That's not a scary bug. That's the framework doing your shape checking for you. And the fix is usually a single reshape. And that's the math layer, element-wise, matmul, reductions, broadcasting. But here's the thing, we've only described forward math. A model doesn't just compute, it learns. It figures out how to nudge every weight to be a little less wrong. How does it know which direction to nudge? That's calculus done automatically. Next time, Autograd. Okay, into the file. It's called tensormath.py, 2 pages. Top to bottom, we make 2 small tensors, run element-wise ops, do a matmul, take some reductions, broadcast a bias, and then deliberately break it and fix it. Every line prints something, so you can see the shape at each step. First we set a manual seed and build our tensors. Torch.arrange gives us a flat range. Reshape folds it into a 4 by 3 matrix A, and we make a second 4 by 3 matrix B the same way. Setting the seed means if you run this at home, your numbers match mine exactly. Element-wise block, a plus b adds cell by cell, a times b multiplies cell by cell, and torch.xp raises e to the power of every element. Print the shapes and notice they're all still 4 by 3. Element-wise never changes shape. Matmul. To multiply a by something, the inner dimensions have to agree, so we make a 3 by 2 weight matrix W. I at W is 4 by 3 times 3 by 2. The 3's match and cancel, leaving 4 by 2. The print confirms it. This single line is a neural net layer in miniature. Reductions. A dot sum dim 0 collapses the rows and gives a length 3 vector, 1 sum per column. A dot sum dim 1 collapses the columns and gives length 4, 1 per row. Then the same idea with mean dim 1, keep dim true, and watch the shape become 4 by 1 instead of just 4. That stub dimension is what lets the next line work. Broadcasting. We make a length 3 bias and just write a plus bias. No loop, no tiling. PyTorch lines the shapes up from the right, 3 matches 3, and stretches the bias down all 4 rows. Output stays 4 by 3. This exact pattern is how every linear layer adds its bias. Now the deliberate landmine. We make a length 4 vector bad and try a plus bad. The rightmost dimensions are 3 and 4, they don't match, and neither is 1. So PyTorch refuses and raises a runtime error. We wrap it in a try except and print the message, so it doesn't crash the whole script. And the fix on the very next line, reshape bad to 4 by 1. Now the shapes are 4 by 3 and 4 by 1. Line them up from the right, the 1 is allowed to stretch, and it broadcasts across all 3 columns cleanly. The result comes back 4 by 3, 1 reshape, bug gone. That calm red and fix loop is most of what working with Tensors actually feels like, so we can compute forward all day. But how does a model learn to be less wrong? Next episode, PyTorch does the calculus for us, Autograd.